Semiconductor manufacturing has hit a thermodynamic boundary. Moore's law relied on scaling transistors across a flat, two-dimensional silicon wafer, but at current densities, 2D processing chips overheat and throttle under intense workloads. This thermal limit exposes a structural flaw in the von Neumann architecture. Since the earliest mainframes, computer design has physically separated the logic calculation cores from the memory storage banks. To perform a calculation, data must travel from memory to the processor across a wide motherboard bus. In modern hardware, the physical transit of that data requires significantly more time and energy than the arithmetic calculation itself. This creates the memory wall. Large language model inference requires pulling hundreds of billions of weights from memory for every generated token, resulting in massive power draw and severe thermal throttling. The silicon industry cannot expand the die footprint horizontally to alleviate this congestion. Moving the data is now more expensive than computing the data. Monolithic flat silicon has reached its maximum viable scale for artificial intelligence. Restricted from accessing advanced extreme ultraviolet lithography equipment, Chinese foundries abandoned the pursuit of smaller monolithic nodes and pivoted entirely to vertical three-dimensional wafer-to-wafer integration. This shift is driven by specific manufacturing innovations, including Huawei's LogicFolding and YMTC's Xtacking architectures. Instead of putting memory and logic side by side on one surface, foundries manufacture the high-density memory arrays and the peripheral CMOS logic circuits on entirely separate wafers simultaneously. They then use direct copper-to-copper hybrid bonding. The two wafers are polished to an ultra-flat finish, flipped face-to-face, and joined at room temperature by spontaneous van der Waals forces, completely eliminating the need for traditional solder bumps. A low-temperature anneal forces the copper pads to expand and interdiffuse into permanent interconnects. This process shrinks the wiring paths between memory and compute from millimeters down to sub-10 micrometers. This vertical density enables processing in memory. Thousands of micro-logic arithmetic units can be embedded directly inside individual DRAM vaults, nearly eliminating the need to move data across an external bus. The semiconductor physics have successfully achieved three-dimensional spatial hardware, yet standard artificial intelligence software is still instructing that hardware to operate in two dimensions. Standard deep learning frameworks, including PyTorch and ONNX, are built around flat linear memory models. They expect uniform precision and sequential layer passes. Executing one of these models on an embedded edge device requires compiling massive C++ toolchains and integrating heavy Python runtime environments. Frameworks rely on foreign function interfaces to talk to bare metal C libraries. Crossing this boundary into external libraries exacts a heavy computational toll. Each invocation introduces a delay to acquire scheduler locks and coordinate states. Even minor stack misalignments here trigger fatal segmentation faults. Welvet AI addresses this latency by bypassing the C interface entirely. Its core execution paths are written in pure Go and handwritten Plan 9 assembly. Utilizing the Plan 9 assembler permits direct, low-level hardware interaction. The code executes natively without relying on heavy external compilers like GCC or Clang. In autoregressive generation, a model performs millions of rapid function calls to generate a single sequence. Bypassing the 200 nanosecond delay per operation removes a crippling structural bottleneck. To mitigate the memory bandwidth problem, developers are compressing data using extreme sub-byte quantization formats, such as 4-bit block quants or 1.58-bit ternary representations. Legacy frameworks struggle with mixed precisions. They silently inflate these sub-byte values back into 32-bit floating point numbers in system memory right before executing the math. This silent type coercion forces the hardware to move bloated data anyway. The energy efficiency and memory bandwidth advantages the quantized format was designed to provide are erased. Welvet enforces absolute strictness regarding storage truth. It operates natively across 34 numeric types and 20 quantization formats, without retaining a 32-bit master weight. The system uses a short-lived unpack scratchpad to calculate updates within native constraints, running all formats through a single unified MATVEC microkernel. Extreme sub-byte ASICs and heterogeneous vector lanes receive instructions exclusively in their native numerical language. developers are forced to confront the true speed, size, and quality trade-offs inherent in hardware-level sub-byte optimization, free from hidden emulation. Since the inception of deep learning, neural networks have been programmed as directed acyclic graphs, strict one-dimensional and two-dimensional linear layer sequences. Attempting to map a flat layer pass onto a three-dimensional memory vault incurs massive routing delays. Welvet replaces flat graphs with a volumetric grid architecture, mapping networks onto a spatial XYZ coordinate space defined by depth, rows, and columns. A single spatial cell in Welvet corresponds directly to an isolated microvault inside a physical 3D memory stack. Sequential execution models fail when encountering dynamic, cyclic feedback loops. They deadlock trying to process multi-directional signal hops between spatial nodes. Welvet discards the standard forward pass for a discrete time-step mesh. Network cells update asynchronously from a double-buffered state, taking forward across discrete time steps. Data sent across a remote link arrives at a neighboring coordinate on the exact next tick. Complex, brain-like recurrent mesh topologies require a discrete time-spatial engine to run deterministically on event-driven neuromorphic processors. The engine combines zero-CGO assembly, strict sub-byte storage truth, and a volumetric step mesh into a single primitive. By abandoning heavy C++ runtimes and eliminating external dependencies, Welvet compiles into a single, fully static binary for any target OS or hardware architecture. Systems engineers can deploy hardware-accelerated inference models natively into air-gapped, sovereign edge environments without managing complex compiler suites. The footprint is small enough to operate on orbital satellite buses and strictly regulated implantable medical devices. It also scales upward to handle high-throughput cloud operations. Chinese data centers are already utilizing 3D near-memory architectures to transcode video and process AI directly at the hardware layer. To guarantee absolute reliability across these varied platforms, an external validation harness confirms that over 200,000 matrix cells execute identically on the physical silicon, explicitly rejecting unsupported formats rather than resorting to silent host emulation. The von Neumann limits of two-dimensional scaling have forced silicon hardware into the third dimension. The von Neumann bottleneck will only be closed by an artificial intelligence software stack explicitly designed to inhabit spatial topologies.